All right, so last class we started this lesson, and so remember where we were before is we were talking about sine and cosine, and we used some formulas that reduced powers down, and we had some guidelines on how to do that. We're going to do the same kind of thing this time. It was secants and tangents, and so the first guideline, I guess is how we're describing them, talks about secant. So if you have the power on secant is even, then you're going to save one secant squared value for du and convert the rest into tangent. And the reason that you might want to do that is because what is the derivative of tangent? No one remembers.
Just regular secant?
The derivative of tangent is secant squared, okay? Which reminds me that some of you need to come in and do some basic skills retakes for me. Aaron, to start with from the beginning, but the rest of you, they're all posted out online, so if you want to go take a look out on Jupyter, you can see whether or not you do in fact need to come in and how close you were and whatever. And of course we'll do, just like we did last time, you can repeat taking that several times if you need to. All right, so the reason we're saving a secant squared here is because the derivative of tangent is secant squared. So if we had one secant squared in the problem and everything else was in terms of tangent, I could let u be tangent, and I could let du then be secant squared. Okay, so that's why that's going to work for us. If the power on tangent is even, we're going to save one secant tangent factor. Any idea why? And then change the rest into secant. Why would we want to do that? Because that's the derivative of secant. The derivative of secant is secant tangent. So it's the same issue as number one, it's just that it's the derivative of secant instead of the derivative of tangent that we're going to be dealing with. It has to do with how we're going to be defining our u substitution, right? So if u is secant, then I need the derivative of it, namely secant tangent, to be in the problem somewhere. All right, so of course the other issue then is, okay, so what if I don't have a secant even and I don't have a tangent even? So if there's no secants, okay, so if there are no secants at all, and the power of tangent is even, I feel like that's, yeah, okay, and the power of tangent is even, then we're going to convert tangent squared into secant squared. That should say odd on one of them. This one should say odd. Let's fix it. It's like one of them needs to be odd. It's number 2. Please fix that. Apparently got on the wrong line when I was typing this in. The second one is if tangent's odd. Okay, so then that explains then on number 3, of course, why if there's no secants, then we're not in case number 1. And if the tangent is even, then we're not in case number 2, or guideline number 2. So what do? Well, we convert a tangent squared into a secant squared value. And then we actually will end up having an even secant in the problem, and then you can go back to problem number, step number 1. Okay, everybody with me? Okay. Okay, so guideline number 4 talks about what happens basically if we only have secant in the problem. So if we have an integration of secant to the m of x, and in particular if that were in fact an odd value for m, because if it were an even value for m, we could use step number 1, okay? So in particular, if this were an odd value for m, we can use integration by parts. And integration by parts is not a normal thing that you would want to try on that because I don't see any parts, right? I don't see any multiplication. I don't really even see a whole lot. I mean, there's a little, but I don't see a whole lot of chain rule involved at that point. So that's an unusual situation, right? It doesn't really look like what I normally would use an integration by parts problem for. So that's why it's written as its own separate little guideline. And then, of course, this is what happened in Trig when we were doing Trig identities. When all else fails, what do? You try sines and cosines, right, and see what you can do with it from there. So mostly steps 1 through 4 will take care of everything we need. But if you run into something that you're just not having any luck with being able to handle, sines and cosines, you know how to change them into sines and cosines. At least I know some of you do because you took Trig with me. We did it. You can go back to that sort of a thinking, is changing everything to sines and cosines and see if everything will work out nicely. All right, so we're going to do some examples of this. The first one that you see is an integration of secant to the 6th of 3x. And this can be done with case number 1 because the secant power is even. So technically, could we use case number, what was it, 4? Yes, but it would end up being overkill, and I don't want to use integration by parts if I don't have to. Are you with me on that? Mm-hmm. I mean, we got more work involved if we do. So if we could avoid it, that would be nice. All right, so that step right there, guideline number 1, says that what I'm going to do is I'm going to save a power of secant squared, right? So one of these secant squareds is going to be saved, and I'm going to save it at the end. I'm going to save it there anyway with the dx, because I know that the point in me saving it is that all of this is going to be at least a portion of the du that I'm going to get eventually. Okay? So what I have left here then at the beginning is what? Secant, what? How many secants do I have left? 4 of them, right? Because I had 6 of them to start with. I pulled 2 of them out. There are 4 of them left. So I have a secant to the 4th left over. And then if you look back there at guideline number 1, what does it say we're going to do with everything that's not the secant squared that we saved? What did it say? Turn them into tangents. Now, I gave you an identity sheet that had a relationship between tangent and secant on it. What was it? If you don't remember, you can grab it, but if you do, now's the time to let me know. Okay, so somebody's going to check for me and make sure that we got the +1. Is it really +1, Hannah? You sure? Okay. I can remember where the +1 goes. All right. So if you're taking a look at this then, we have the right-hand side of this, basically. We've got secant squared. Well, sort of anyway. All right, we'll deal with it in a minute. But we've got something in terms of secant. So we should be able to take this something in terms of secant and rewrite it as tangent squared plus 1. Now, I said we sort of have tangent squared or secant squared, and we do sort of have it, because what we really have is we really have secant to the 4th, right? Let's try that again. But one of the properties of exponents that you can remember that would be helpful at this point is that when you square something twice, it's the same as the power 4, right? If you have a squared squared, that's a to the 4th. Property of exponents. So secant to the 4th is really secant squared squared. And now the part that's in the parentheses, I can change it into tangent. So this I can change into tangent squared of 3x. Don't forget it's 3x in this particular problem, plus 1. And it's that quantity squared. Is everybody good so far with that? Okay, it feels a little awkward. It'll feel better once we have done more of them. But at some point in here, and it doesn't really matter where you do it, so if it bothers you to work with the trig functions, just because they're a little bit cumbersome and messy, you can do it early on. I'll do it early on in this problem. We know that the goal, anyway, at some point here, because we're in case 1, is to let u be tangent of this value. So in this case, tangent of 3x. And then du, the reason we want that is because we saved the secant squared 3x at the end for this purpose. Because the derivative of tangent is secant squared. But I have secant squared 3x here, not just secant squared x, right? What's the derivative because of that 3x that's inside? What happens? Right, I have a 3 on the right-hand side, right? Because I have to take the derivative of the 3x, it's chain rule, which means this is going to be thought of as 1/3 du is the secant squared 3x dx. So I'm going to take this step right here where I am, and I'm going to put the 1/3 in here. Here's my integral. I've got tangent squared. Well, that would be u squared plus 1. All of that squared. And then this portion gets replaced by du and the 1/3 that's in front, which I already did. You have to let me know if you have any questions about where any of that came from. All the pieces okay? All right. Now we have some algebra, because I still have something in parentheses with a squared on the outside, don't I? So from algebra, what you remember is that you actually have to multiply that out. And you guys do remember that, right? Say, well, of course, Dr. Hands. Of course I remember that. All right, so what do I get? What is u squared plus 1 times u squared plus 1? Close, 2u squared. And then plus 1. First, outer, inner, last, right? So the first terms give me the u to the fourth. The inside gives me u squared. The outside gives me u squared. So I get 2u squared, and then the last one gives me 1. And I can integrate that, and I know you can too. Whoops. All right, so what did you get for your integration? I gave you time to think. That's why I was doing all that. What's the integral of u to the fourth plus 2u squared plus 1? Plus u. And then, of course, plus c's, which you guys did a really good job remembering those on your basic skills quiz. That was good. Plus c, right? I don't think there was numbers at the front of this, were there? Am I done? No, there's actually 2 things I need to do. One of them would be to distribute the 1/3 through, but what else do I need to do? I need to plug that value back in for u, right? All right, so this is 2u to the third over 9 plus u over 3 plus c. All right, so what was u? It was. So this is tangent of 3x to the fifth, so we could actually put the fifth right here. So tangent of the 3x, the 5 in the middle, right, over 15 plus 2 tangent cubed of 3x over 9 plus tangent of 3x over 3 plus c. And I will be happy as a lark if you get to here. I don't need any more simplification or combining these terms. I don't even need you to factor out what they have in common. This is good. This is good. All right? Your back of the book may do a little bit more with simplifying things like factoring out or something or getting common denominators. Really, it's fine. Okay? Any questions on this one? So that was a guideline number 1 problem, basically, right? The secant power was even. All right, let's take a look at the second one. Secant to the fifth of x tangent cubed of x dx. And we've got to figure out first which of the guidelines I'm in. Is it guideline number 1? Why not? Secant's odd, right? The power on secant's odd. Is it guideline number 2? It is once I fixed my guidelines because they were messed up to begin with, right? Yeah, that's right. Once I fixed my guidelines, now it's guideline number 2. I do have a tangent with an odd power here, which is what guideline 2 has for me. So I am working with guideline 2. So what does guideline 2 say I'm going to do? Okay, so I'm going to save a secant tangent back here. And this one just is secant x, tangent x. I don't have to worry about any multiple angle inside there. And then let me write out what's remaining at the moment, and then we'll look at the other portion of what the directions say. So how many secants are left? 4. You got it. And how many tangents are left?
2.
There are 2 left. Okay, so is everybody okay with that break apart step? Because nothing in the guidelines tell you how to break things apart. Okay, got to break it apart, and then I want to use what the guidelines say. And the guidelines say I'm going to turn everything into something. What am I going to turn everything into? Secants. So in other words, I need to somehow get this tangent squared to go away. Well, I've got a wonderful formula still up here on the board that tells me how to do that. At least it almost does, right? It's not actually written in the form that would be most helpful, but I can change that. I can find out what tangent squared is. So what is tangent squared of my angle? You got it. It's secant squared of theta minus 1. So I can take that tangent squared of theta or tangent squared of x in my problem and I can replace it. So I have my integration at the beginning. I have my secant to the fourth. That doesn't change. But my tangent squared changes into secant squared of x minus 1. And then again, I have that secant x, tangent x at the back. I'm going to go ahead and multiply this out in the secants, just because I didn't do it from that perspective last time. So if I take this and I distribute, what is secant to the fourth times secant squared? Secant to the sixth. We add exponents. It's secant to the sixth of x. And then I have minus secant to the fourth times 1. Well, that's just secant of x to the fourth, right? And all of that is actually still multiplied by this secant x tangent x dx. And I do not want to distribute that secant x tangent x out. That would put me back closer to where I started with. The whole point was to get that out at the end because that's going to be part of the du. So in no case in anything I'm doing, I'm going to mess with this piece. I'm going to leave it alone. And the reason I'm going to leave it alone is because this is a u substitution problem. My u value, the whole point in saving that secant x tangent x is because I want my u to be secant of x. And I want that because the du, the derivative of secant, is secant x tangent x, right? So I can take my integral then, and what will my integral look like? What will secant of x to the sixth become? U to the sixth. And what will secant of x to the fourth become? U to the fourth. And all of that is actually multiplied by secant x tangent x dx, which becomes du, right? All of that becomes du. Okay, but now I'm ready to integrate. This one's actually cleaner than the last one. I didn't have to do as many steps to get here. All right, what is the derivative of u to the sixth? Sorry, the antiderivative of u to the sixth. Yes, good. U to the seventh over 7. And the antiderivative of u to the fourth? Perfect. Thank you, Kendra. Fifth over 5. And then I need a plus c on this, right? And I am not far from being done. Did I? Let's see. Yeah, I didn't leave myself another slide for this because I knew it wouldn't take much longer. Okay, so I'm out of space down there at the bottom. Almost. Let's see if I can try this. One way or another. It's all running into each other now at the bottom, but you saw it before it did. All right, so the u, of course, is secant x, so I need to get that back in there, right? So I will put my fraction in front. This is 1/7 secant to the 7th of x minus 1/5. You can still leave them as division on it if you want, but I'm out of space. Secant to the 5th of x, and then plus c. Is that okay? So it all boils down to u substitution, right? Until we get to here. Because which case is this? Which guideline am I going to have to use? Yeah, number 4, right? I think it was 4, wasn't it? Integration by parts. Because I have a power of secant. That's the only thing that's present. But my power of secant is odd. So it told me I'm supposed to use integration by parts, rather, u du, v dv. And I'm supposed to let dv be secant squared. I think that's what it said, right? So if dv is secant squared of x dx, what is u? secant x. Right, I have 3 secants, secant cubed. I've got 3 of them. They've all got to go somewhere. 2 of them went down in dv. The other one's going to go up in u. Right? Okay, so the reason, of course, that we let secant squared be the dv is because I know it's antiderivative. What is the antiderivative of secant squared? It's tangent. Okay, so I wouldn't want secant to be in the dv spot because then I have to use one of those strange ones that I think involves natural logs on your sheet, and I don't want to get natural logs involved in the problem on purpose. Right? I mean, if they are involved, that's one thing, but I certainly don't want to try and involve them. Now, I do need to know what the derivative of secant is. So what is the derivative of secant? Right, we did that one a little bit ago. So the derivative of secant is secant x tangent of x dx. Okay, so u times v, right? We go across the top. That would mean I have secant x tangent x minus. Now I cross the other diagonal, right? Bottom left, top right. So I have tangent squared of x, and I have secant of x written in either order. Okay, so we can ignore the secant x, tangent x. That part at the beginning is finished. Now I've got a antiderivative of tangent squared secant. Yeah? And I need to decide what I'm going to do with that. Well, it's not guideline number 1, right? Because I don't have an even power of secant. It's not guideline number 2 because I don't have an odd power of tangent. So what do I do? Well, I'm going to use the Pythagorean theorem up here on the board, the one that I've been using at this point to convert things. And I'm going to turn this tangent squared back into secant squared. Okay? And you'll see why very quickly. So I want to take this tangent squared and I want to replace it with secant squared. So right now I have secant x tangent x minus the integral. And tangent squared is secant squared of x minus 1, and then times the secant of x dx. All right, give myself a little bit more room to work. So secant x tangent x minus. Now we're going to distribute this out. So I've got secant squared of x times the secant x on the outside makes secant cubed of x. And then the negative 1 would make negative secant of x dx. Suggestions? What's going on now?
You got what we started with?
Almost. I have a portion of what I started with, right? But only if I separate my integral. So let's separate the integral, all right? So I have secant of x, tangent of x. I have minus the integral of secant cubed of x dx. And then I've got a negative in front of that integral and a negative inside, making this a positive integral of secant x dx. So the portion that Cameron's talking about is that this piece looks exactly like what I started with, doesn't it? The part at the end doesn't, though. What am I going to do with that? What am I going to do with the integral of secant of x dx? Yeah, and you have a form for it, don't you? I think it has natural logs in it. So you have a form that actually works for the very ending part of that. So let's use that form first, and then we'll do the addition to the other side like we did with the example that I just erased from underneath the screen, right? Okay, so I have secant x, tangent x, and then I'm going to do plus, and I'm going to do the integral of the secant x next. Okay, so I'm going to put this integral that I don't have dealt with at the back for the moment, just switching the order. All right, so somebody's going to look on their sheet for me, and you're going to tell me, what is the antiderivative of secant x? That sounds right. All right. Okay, so when I get to this point and I recognize that a piece of it is just like what I started with, I have to write it in an equation form, which is exactly what we did earlier today. We wrote the secant of x cubed on the left, and I've got it on the right. So unlike the one that I started with now, I just have negative of this, so the only thing I have to do is add a positive one. So plus the integral of secant cubed x dx. So how many of them do I have on the left? 2, yeah. 2 times the integral of secant cubed of x dx equals secant x tangent x plus the natural log of secant x plus tangent of x. And I need a plus c on there somewhere, so let me put it there. Now we have to do one more thing. What do we have to do?
Divide by 2.
Yeah, that 2 in the front, it can't stay there, right? I'm supposed to be solving for the other portion of it. So divide by 2 or multiply by 1/2. I end up getting that the integral that I was looking for, which is the secant cubed of x dx, is 1/2 secant x tangent x plus 1/2 the natural log of secant x plus tangent x. Be careful not to lose the plus your c at the end. So you've got integration pi parts in there, and then you end up changing it using the Pythagorean identity so that you can use our trick, right? And Cameron saw it because we talked about the fact that it was going to be coming up again, and you notice it when it looks exactly like where you started with. It may or may not have the same sign. It may or may not have, a 2 or something in front of it or whatever. That's fine, but the rest of it will match. The integration itself will match. All right, product to sum formulas. In your book, I will tell you, present these a little bit differently. It just uses a little bit different notation. I think this is a little bit cleaner, so this is the one that I chose to write in your notes. These are properties that allow us to reconcile different angles. Notice if we were doing things with u substitution or integration by parts, I really can't deal with the left-hand side of any of these equations very well. Because if one of them is u, the other one is not going to be du, because their angles don't match. And that's a problem. So if I can't make the angles match, which I can't, the best thing I can do otherwise would be to separate the multiplication into addition. Because if the multiplication were written as addition or subtraction, then I can separate the integral. And I can work with that just fine. So these formulas right here are really easy to use. Okay, so you ready to try one? So we noticed on example number 3 that we are in the case that would use these because I have sine and cosine, and I have different angles. Everybody good with that so far? Now, you can deal with these exactly like they are. That is to say, the negative, you can work within there and let the negative be in there. I'm actually going to pull the negative out in front, and I can do that because if you remember the trig identity sheet I gave you, there's an even-odd identity on there that says that sine has the property that the sine of negative the angle is equal to negative the sine of the angle. And from trig, that has to do with the fact that sine is an odd function. Okay, it has origin symmetry and all of that good stuff. So I'm actually going to pull the negative to the front because then I don't have to deal with any negative angles. I'm just going to be, dealing with positive angles, which is just one less thing to keep track of. That's really what it amounts to, okay? So negative sine of 4x cosine of 3x dx. All right, so looking at the three I don't have mine with me here, but looking at those three product of sum formulas over here, which one are we in? 1, 2, or 3? I didn't number them on here, but you can count. So, which one? 2. So the first thing I am going to do is I'm going to have a 1/2. So I'm going to just put the 1/2 in front with that negative because I don't really need it to be a part of the integration. It's just part of the quality or quantity that I have. And then it says that I'm supposed to take sine of the first angle, 4x, minus the second angle, 3x. And then I've got a plus, and I've got the sine of the first angle, 4x, plus the second angle, 3x. And all of that is the portion I'm going to take the antiderivative for. All right, so I think we can simplify those pretty quickly. I have negative 1/2 the integral of sine of what? X plus sine of what? 7x dx. How come when I copy and paste, it always copies just one extra thing that I needed it to copy? Okay, so we're going to do the antiderivative then. All right, so what's the antiderivative of sine of x? Negative cosine of x. And what's the antiderivative of sine of 7x? Right. All right, anytime you have a multiple angle, it ends up being division when you take the antiderivative. If you were taking the derivative, it would end up being multiplication, right? Chain rule here, right? Okay. And then I have a plus c on here at some point. I can distribute with my negative 1/2, which is just great that it's negative now because I'm going to end up having no negatives, aren't I? This is 1/2 cosine x plus, I'll write it as 1/14 cosine of 7x plus c. Any questions? So the sum to product formulas, or sorry, these are product to sum formulas are really easy to use. All right? They ended up with having nothing that had any use substitution or integration by parts or anything, right? It's just an application of trig. I told you there were applications of trig. Okay. Any questions in this section?